All right, so in the last lecture we were using a list and we looked at this problem called jump it. And so in jump it, you had this board that was represented as a list. You're trying to make it from the left-hand side of the board to the right-hand side of the board, or from the start of the list to the end of the list. So now there's a similar problem you can look at that is a little bit harder to solve, but still, you can still approach it in a similar way that we approached the jump it problem. So in jump it, we came up with a recursive solution for the problem. Now, the jump it problem, the rules of that particular problem made it impossible to move to the same square twice, and it also made it impossible to fall off the board. And if you put those two things together, that basically means is that after every step, you're solving a smaller version of the original problem. And so that makes it a very good candidate for a recursive solution. If you relax these two rules, it's no longer clear that you can solve this problem recursively, or solve the next problem recursively, sorry. Okay, so it's a similar idea. You've got a list. It contains a bunch of non-negative integer values in it. The rightmost element is always 0. The leftmost element can be any value, and you always start at the leftmost element. So the goal is to try to reach the rightmost element, so try to reach the end of the list. But the number or the element in each location of the list, that tells you how many positions you can move left or right. So for example, the 2 here means you can go to the 3 or you can move to the 2. And so now you can move left and right on the board. You're not allowed to fall off the board. So if you're at the 2, you're not allowed to jump 2 squares to the left because you fall off the board. All right, and so just to sketch a quick solution for this particular board, you can do the following. So you start at the leftmost square. You can only move 2 squares to the right. You can't move 2 squares to the left, so we go to the 4. Right? When you reach the 4, you can't move 4 squares left, but you can move 4 squares to the right. And now you have a decision to make. So when you reach the 1, you can either go to the 6 or to the 2. And so for the first solution, I'm going to go to the 6. You reach the 6, you can't go right, so you have to go left. You're at the 3, right? And at this point, you say, well, you're not really making any progress, right? I made it all the way to the 6, and now I'm all the way back at the other end of the board. But if you keep on going, you'll realize that you can, in fact, find a solution to this particular board. There is a different solution. There's probably many different solutions. So again, starting at the 2, you go to the 4, then to the 1. Instead of going to the 6, I can go to the 2. And now when I go to the 2, I can go left to the 2. Notice that when you hit this square here, one of your choices is to go back to the square you were just on, right? But if you do that, you just end up going in circles. So you want some way to avoid visiting squares that you've already been on in this particular version of the problem. All right, so from the 2, I go to the 3, and now we know the solution. You go to the 5, and you go to the 0. And there probably are other solutions on this board. So it is possible to find what are called cycles, where a move takes you back to a square that you've already visited. So this is a very simple cycle, right? You're just going, you're going back and forth between these 2 squares, right? But you could have a more complicated cycle. So for example, you go to the 2, and then you can go somewhere, then you can go somewhere, then you can come back to the 2, right? Or you can come back to the other 2, and that still leads you to a cycle. So if you have a cycle on a board, you can easily make a board where no solution exists. Right? So on this board, you just go back and forth on the 2, and you never reach the 0. Right? So you want to be able to detect issues like this. Right? And similarly, on this board here, it doesn't matter what sequence of moves you make, you eventually end up in a cycle of some kind. Right? The fact that the numbers are 2s is just because I don't have that much room on the slide. Right? You can create a cycle using any values on the board. All right, so even without a cycle, it's possible to have a board where no solution exists. So on this board here, you start at the 1, and then you go to the 100, and then you're stuck, right? You can't go 100 spaces to the left, you can't go 100 spaces to the right. So there's no solution on this board. All right, so if you analyze the problem and you compare it to the previous jump it problem, you'll realize that it seems like in this particular problem, the board doesn't get smaller in any obvious way. right? It looks like that when you move to a square, you can always come back to that square, right? So you're never removing squares from the board like we did in Jump It, right? So in Jump It, you can never move left, so every time you move to the right, you eliminate all the squares on the left. I claim, in fact, that this board does, in fact, get smaller at every step, right? And so the reason it gets smaller at every step is because every time you step on a square, you never want to come back to that square. So in fact, every time you land on a square, you're removing the square that you're currently on. So the board does, in fact, get smaller by 1 square at each step. Now, in the previous version of the problem, we made the board smaller by computing a sublist, right? So we throw away all the squares to the left, and you're left with the squares to the right. In this particular case, we don't have that luxury, right? I can't just use a plain old sublist because a sublist is a contiguous part of the list, right? If you're in the middle of the board, there's no way to compute a sublist that doesn't include just the middle square. You could grab 2 lists and mash them together, but we want to avoid that. So we need some other way to indicate that we've landed on a square before. And so the way I'm going to do that is I'm going to change the board. Every time you land on a square, we're going to remember what the value of the square is, and then we're going to set the value of the square to some invalid number. So for example, we'll set it to a negative value. Right? That way, if we come back to that square, we know that we've been there before. There are other ways to do this. You could keep a second parallel list, same size as the original board, and you can set it to a bunch of Boolean values. So you can set it to all false. Right? Every time you land on a square in the parallel list, you just set the corresponding element to true to indicate that you've been on the square before. Right? And there's other ways you can solve this particular problem. All right, so, also like the previous problem, it's not obvious how you would solve this problem using a loop. Right? And so I'm going to right away approach this problem recursively instead of iteratively. All right, so in the previous problem, we found the base cases first. When you're solving a recursive problem, you don't have to find the base cases first. You can always try to solve for the recursive cases first if you want to, and then go back and figure out what the base cases are. So I'm going to approach the problem this way. All right, so our recursive cases are you land on a square somewhere. Right? It doesn't matter if you're the first square, the last square, middle square somewhere. You're on a square, and it has a number. You want to ask the question, can you move to the left? Right? So if you can move to the left without falling off the end of the board, then you want to ask the question, well, can you solve the board by moving to the left? Right? So that's going to be one of our recursive calls. There's a second recursive call. Right? You're on a square. Your other choice is, can you move right? So if you can move right, you want to ask the question, can you solve the board by moving to the right? Right? And so our method is going to answer the following question. Can you solve a board? Right? All right, so here is our method. It's called isSolvable. It returns true or false. Right? True if the board is solvable, false if the board is not solvable. Right? And it returns true or false given this, the location of the board that you are currently on. So index is the index of the list representing the square that you're currently standing on. First time you call the method, you're going to pass in 0, right, to indicate that you're on the left-hand side of the board. Our board is just a list of integer. You can replace this with an array list of integer if you like. Right? So it's an array list of integer. Up here, notice that the method says it does not modify the board. So what it's trying to tell you is that if someone calls the method and they pass in a board, when the method returns, as far as the caller can tell, the board that they get back is the same as the board that they passed in. Right? This is probably the nicest thing that you can do for the user. Right? If someone gives you a board representing their game, you don't want to mess up the board and replace it with, replace the squares with different values. Right? Whoever's using the method is probably not expecting you to change that thing. And so our method promises not to modify the board. Or at least it promises not to appear to modify the board. As you'll see, we are in fact going to modify the board. Right. All right, so recursive method. So we're going to have some base cases, but we aren't starting with the base cases first. We're going to start with the recursive calls. remember that our recursive call is, can I move to the left and can I move to the right? Right? And if so, solve the board moving left, solve the board moving right. So I need to know how many squares can I move, right? And so the number of squares that you can move, that's given by the board, the square that you're currently on. Right? So I ask the board to get the value stored at that index. All right, so I need to indicate that I've already been on this square before. And so I'm going to go into the board and I'm going to change it. Right? So I'm going to set the board location at that index to -1 to indicate that I've been on this square before. Right? Now remember, the method promises says it's not going to do this. It's not going to permanently change the board. So I have to remember to unset the board. I have to put it back to its original state when I'm done. Right? So later on, somewhere down here, we're going to unset the board back to its original value. All right, so can I solve the board by going left? So when left is set to false, it'll be true if I can solve the board by going to the left. Right. All right, so can I move to the left? So you can move to the left if you can take that many steps from there, right, to the left. So moving to the left means make the index smaller, right? So index minus value is my new index, or is the index to the square to the left, right? Is it a valid index for the list? So is it greater than or equal to 0? If the answer is yes, then you might be able to solve the board by going left, right? So how do you solve the board by going left? Well, you just recursively call is solvable, right? So remember, is solvable promises to solve that board given that index, right? So there's my new index, is index minus value, right? There's my board. Now remember, I've modified the board to indicate I've been on a square before, right? And so we're going to use that information in our base cases. And so we make our recursive call is solvable, and that tells us whether or not we're going to be able to solve the board by moving left. Similarly, I want to try going to the right. So can I move going to the right? We start by setting that to false. Right? Now, what is the index of the square to the right after moving that many squares? Well, it's just index plus value. So is that a valid index for the board? It's a valid index if it's less than the size of the board. So if that condition is true, I'm going to try to solve the board by moving to the right. And I'm just going to call is solvable to solve the board formed by moving to the right. Right? So take that many steps to the right and solve the new board. Right? If either one of those conditions is true, we know that the board is solvable. Right? So the board is solvable if when left is true or if when right is true. Right? So I'm just going to combine those with a Boolean expression and return that value there. Now, we have to remember that the method promises not to permanently modify the board. So after I've determined whether or not you can solve the board by going left or by going right, then I unset the board. Right? So I unset the board and put it back to its original value, right? And then I'm done. All right, anybody have any questions about how the recursive calls work here? Okay. What about the base cases? So it's a recursive method. We need some base cases to stop the method. All right, so what are our base cases? Well, one of the obvious base cases is if you reach the right-hand side of the board. Right? If you reach the end of the board, well, you've solved the problem and you know the answer is true. Right? The other base case, so if you have a recursive method that's going to return true or false, there's probably two base cases. Right? There's one base case that returns true. We've got that one. There probably is also going to be a base case that returns false. Right? And so we know the board is not solvable if you end up in a cycle. Right? So if you reach a square whose value is -1, you know the board is not solvable. There's another hidden base case here. Right? The other hidden base case is whether or not you can win by going left or right. Right? So if you, the other time this method can return false if win left and win right are both false. Right? And so there's sort of another hidden base case here. All right, so how do you code it the base cases? Well, it's easy, right? You reach the last square, so that just means is index equal to the size of the board -1, right? You reach the square whose value is -1, well, that's easy. That's if value is equal to -1, right? And so there are your base cases. Right? So if the current square that you're on, if its value is less than 0, we've been on the square before, so we can't solve the board. We can't solve the board with this move, right? Similarly, if you land on the last square of the board, well, you've solved the problem, so now you can return true, right? And now the recursive part goes here, and I claim that that solves this particular problem. Right? And so if you code that up in Eclipse or whatever you're coding this up in and run it, you can try it out. It will, in fact, solve the board that I showed you when I introduced the problem. Okay. And so there's an example of solving a similar problem to jump it, again, using a recursive solution. Any questions so far? All right. A little bit more recursion, and then we'll be done with recursion for the time being. Okay, so I would like to now write a method that moves the smallest element in a list to the front of the list, and I'd like to do it recursively. Right? So doing this iteratively is easy. Right? You search the list, right? So you look at every element in the list, looking for the smallest element. Right? After you finish looking at all the elements in the list, you know what the index of the smallest element in the list is. Right? So now you can just swap the index of the smallest element with the, you can swap the element at the smallest index, you can swap the smallest element of the list with the first element of the list, right? So you just switch them, and now you have the smallest element at the front of the list, right? If you wanted to, you could take the smallest element out, and then you can insert it back at the front. But that's an ON operation, right? So removing from the middle of a list is ON, from an array-based list is in ON. You remove the element, you have to shuffle all the elements after it forward one position in the list. To insert at the front, you have to move all the elements in the list one position to the right, and then insert the element at the front. Right? So swapping the two elements is much more efficient. All right, so how do you do this recursively? So it's not that obvious how you do this recursively. So I'm going to draw you a picture and show you, hopefully the picture shows you what's happening here. So here's my original list. For simplicity, it contains the numbers 0 through 9, so it's easy to tell what elements are in the list. Right. All right, so we want to move the smallest element in this list to the front. So we know that we want to move the 0 to the front. Now the question is how on earth do I do this recursively? Right. And so one approach that you can take is you can say, well, suppose I can find the smallest element in the sublist that doesn't include the first element. Right? If I can find the smallest element in this list and move the smallest element to the front of that sublist, right, I end up with the following. Right? So find the smallest element here, which is the 0. I'm going to move that to the front of the list, so the 0 is now here. I don't know what's happening to the rest of these elements, and I don't care. Right? The numbers 1 through 7 and 9 are in those elements. I don't know where they are, or I don't care where they are. Right? All that I care about is that the 0 ends up here. Right? So what do I know now? So I know the smallest element in the blue list is at the front of the blue list. Right? You can imagine that the 8 is a list of size 1. Right? So I know that the smallest element in the white list is at the front of the list. Right? Therefore, the smallest element in the entire list must be one of these two values. Right? So if the 0 is smaller than the 8, I'm just going to switch the 0 and the 8. Right? And that moves the smallest element to the front of the list. Right? The magic here is this step here. Right? I'm going to assume that I can move the smallest element in the sublist to the front of the list. Right? And that's one of the steps you normally have to take when you're trying to come up with a recursive solution. Right? You have to trust that the recursive solution is going to do what it's supposed to do. Right? So my recursive solution will move the smallest element in a list to the front of the list. If I have that solution, I can surely move the smallest element in a sublist to the front of the sublist. Right? And so that's the approach that you take. That's an approach you can take to move the smallest element in a list to the front. Right? So what does it look like in code? It looks like the following. Right? So min to front moves the smallest element in the list T to the front of the list. Right? So we'll ignore the base cases for now. Right? All right, so what was the first step I did? Well, I said, well, I'm going to move the smallest element in the sublist, not including the first element, to the front of the sublist. Right? How am I going to do that? I'm just going to use the recursive method. So I'm going to call min to front, right? And I want to move the smallest element in the sublist not including the first element, to the front of the list. Right? And so after this recursive call returns, we have this picture here. Right? And now it's simply a matter of comparing the first two elements. Right? So the first element is tget0. The second element is tget1. This is a list of integers, so I can write if second is less than first. Right? So if they are, I'm just going to switch first and second. Right? So set the first element to second, set the second element to first, and that's your recursive. There's your recursive part of your method. So what is the base case for this method? So if you have a list of size 0, there's nothing to do. Right? If you have a list of size 1, there's nothing to do. The smallest element is already at the front of the list. So here, our recursive case is if the size of the list is less than 2, do nothing, or return. Right? And I claim that that moves the smallest element in a list to the front of the list. All right, any questions there? So yeah. So you don't know what this thing is going to do to the rest of the elements of the list. It will probably reorder them, but it's not going to remove or duplicate elements. Right? So everything that's in the original list will still be in the original list. Yep. You don't know what the order will be. To figure out what the order will be, you actually have to trace this out with an example. Any other questions? All right. If you can recursively move something to the front of a list, you can sort a list. Right? All right, so let's assume I've moved the smallest element in this entire list to the front of the list, so the 0 is now here. Right? I now have the rest of the list. Right? The rest of the list is probably in some unsorted order. So what if I move the smallest element in the rest of the list to the front of the rest of the list? Right? Well, that moves the 1 into the second position of the original list. Right? So now you have the smallest two elements in sorted order at the front of your entire list. Right? And now you repeat. Right? So I'm now going to call them into front on the rest of the list. Right? So if I move the smallest element in this list to the front, the 2 comes here, and now you've got the first 3 elements of your list in sorted order. Right? Repeat the process again, and again, and again, and again, right? And eventually, you end up with a sorted list. And that is exactly selection sort, right? So selection sort repeatedly moves the smallest element in a sublist to the front of the sublist. Right? You can implement this in like 2 lines of code if you already have min to front. Right? So there's selection sort if you already have min to front. Right? So move the smallest element to the front of the list, and then sort the rest of the list. Right? So the rest of the list is just the sublist starting at the next element. Right? Here I've hidden the base case. So the base case for selection sort is exactly the same as min to front. Right? If you have a list of size 0, there's nothing to sort, so you don't have to do anything. Right? If you have a list of size 1, you're already done. The thing's already sorted. So if the thing is bigger, or if the list is bigger than size 1, sorry, if the list has more than one element in it, then that's where your recursive cases come in. Right? Move the smallest element to the front of the list, and then sort the rest of the list. Right? And so there's selection sort in 3 lines of code. Of course, we've hidden a lot of the complexity in min to front. Right? And so there's an example of a recursive implementation of a sorting method. Right? Assuming you learn merge sort and quick sort in 121, you were probably told how to implement those recursively as well. Right? All right. So you should have also learned a little bit about computational complexity in the previous course, or in your math courses. Right? And so if you want to analyze selection sort, the one way that you can do it is the following. Right? So if you look at selection sort, there's only 2 lines of code, really. Right? Checking if the size of the list is bigger than 1, you can just ignore that for the purposes of computational complexity. Right? So the first step is move the smallest element in the list to the front of the list. Right? And so if you think about how that's going to work, you can realize that you have to look at every element of the list So that's an ON operation. Moving that element to the front of the list is an O1 operation, right? You can do that in constant time. And so overall, that has complexity big O of n. Right? Now the problem is when you analyze this thing, it's a recursive method. So you now have to decide, how do I figure out what the complexity of selection sort is? Right? So the second step is you're recursively going to sort a list of size n minus 1. Right? And so hopefully you know what a recurrence relation is by now. Right? You're going to define the recurrence relation T of n. Right? That's the number of operations needed to sort a list of size n. Right? Then how long does it take to sort a list? So what is T of n? Right? So T of n is just the number of operations needed to sort a list of size n minus 1. Right? That's your recursive step there. Right? Plus the cost it takes to move the smallest element to the front of the list. Right? So that's plus O of n. Right? And hopefully they taught you how to solve this recurrence relation. If they haven't taught you how to do that yet, you'll learn it in 365, probably, the algorithms course. Right? And if you solve that recurrence relation, you'll realize that that leads to a result of big O of n squared. All right, any questions about using lists? Because we're basically done with the lists lectures dedicated explicitly to lists for the time being. Any questions? All right, I guess quickly to summarize, a list is not an array, right? So you can't confuse the two, even though it's tempting. Right? A list represents a sequence of elements where the number of elements can change. Right? In Java, all the elements have the same type. Right? An array represents a sequence of elements, but it's a fixed number of elements. Right? So the number of elements never changes in an array. Just like a list, all the elements in an array must have the same type. The size of an array is given by its field called length. The size of a list is given by its method called size. Right? Using a Java array looks a lot like using a Python list, right? Which is probably the most confusing part if you're a Python programmer. Right? If you want to use a Java list, you have to remember that to use a Java list, you have to use methods instead of the square brackets. Right? So to get an element, you can't write square bracket index. You have to write dot get round brackets index. Right? To change an element in a list, you have to remember you can't use square brackets. You have to use dot set index and then the element value. Right? All right, so those will all come back to haunt you on test 1. Right? So you're going to be asked about lists and arrays on test 1 for sure. Test 1 covers up to the previous lecture, so up to whatever was covered in this set of lecture slides here. So there will be an announcement on OnQ later today. Explaining what's on test 1. All right, if you happen to be paying attention to this page of lectures, you would have noticed that 10 and 11 were struck out. They were struck out for last term. So to create the OnQ for this term, I just copied last term's OnQ. I think we're going to go back and actually look at sets and maps this term because we're a little bit ahead of where we were last term. So I'm going to do the sets lecture now. So in Python, you may have been told what a set was. You were certainly told what a dictionary was. So in a Python dictionary, the keys of the dictionary represent a set of values. So Java also has things like dictionaries. Java calls them maps. The keys in a map are sets. Right? And so a set in Java is supposed to represent a mathematical set. Right? So in math, a set is a collection of unique elements. Right? So no two elements are equal to one another. Right? Sets are useful for doing things like membership testing. Right? So does a set contain a particular value? Right? If you have a list and you'd like to remove all the duplicate elements from a list, one way to do that is take the list, elements from a list, stick it into a set. Right? The set removes all the duplicated elements, because a set has no two values that are equal to one another. And then you can take the elements out of the set and put them back into a list. If you want the mathematical operations of intersection, union, and difference, well, those are also easily done using sets. Right. In languages like Java and in Python, you really kind of need to know what a set is in order to effectively use a map or dictionary. Right. All right, so in sets have no indexing or slicing. Right. But some sets do support returning a subset of a set. So for example, you can make a set of words, and some types of sets let you ask the question, give me back all the words that start with A, or give me back all the words that start with, I don't know, THI, or something like that. So Java has multiple kinds of sets, just like it has multiple kinds of lists. All right, so in Java, if you want a set, you pick between, normally you pick between one of three. Right? So there's something called a hash set. That's the one that's most similar to a Python set if you've used one in Python. You can also choose to use a tree set. So a tree set is a kind of set that sorts its elements in sorted order. Right? So if you have a tree set of words, then you know that the words are all in sorted order. Where's the third one? Oh, there's a third one. The third one is a linked hash set. We'll get to that in a little bit. All right, so sets are similar to lists in Java in that they can hold elements of a single type. So you can make a set of strings, you can make a set of integers, you can make a set of doubles, you can make a set of points, I guess, if you wanted to. So just like with a list, when you use a set, you're going to use the angled brackets and say what the element type is that the set contains. Right. So the fastest set in Java is a hash set. So often programmers will reach for a hash set first. Right. So to make a hash set, you can write a hash set of strings. Sorry, you can write hash set and then string inside the angled brackets. Right. Call the constructor, so a new hash set. In newer versions of Java, you can omit the element type on the right-hand side. So you can just write new hash set, angled bracket, round bracket, round bracket. Right? And that gives you an empty set that you can now populate with some strings. So just like with lists, you can't make sets of primitive type. Right? If you want a hash set, or if you want a set of integers, you make a hash set of integer instead. Right? All right, so what can you do with a set? So it turns out you actually can't do that much with a set. That table here basically summarizes all of the main set operations. Right? So you can make a new set, and so you know how to make a set. It's the same as making a list. Right? You use new, you call a constructor. Right? You can ask is the set empty? Right? So the method is the same as the list method is empty. Right? You can ask how many elements are in the set. So that's exactly the same as asking a list. How many elements are in the list? It's the size method. Right? You can add an element to a set, and that's exactly like adding an element to the end of a list. You just call add. Right? Now sets are different than lists, right? So they're not lists. Right? So when you add an element to a set, for most sets, you don't know where the element will be in the set. Right? All that you know is that it's going to be in the set. You don't know where it will be. Right? When you add an element to the end of a list, you know it's at the end of the list. Right? The exception here is if you have a tree set. Right? So if you have a tree set and you add something to a tree set, you know that it's in sorted order. Does the set contain an element that's equal to some given value? So that's contains, just like with a list. Right? Can you remove an element from a set? Yes, it's remove, and then you pass in the element that you would like to remove, just like you would use with a list. Right? How do you copy a set? Well, you just make a new set, and you pass in the existing set, and that makes you a copy of the set T. Right? So U is now equal to T. They both contain the same elements. If you're wondering why, are all these methods the same as with lists? So it turns out that lists and sets, they both share a common interface in Java. And we'll talk a little bit more about that later on. Right. But if you know how to use a list, you probably know how to use a set. Right? You just throw away all of the elements. You just forget about all the methods that let you do something by index, and that's how you use a set. All right, so when you want to make a set, you have to pick the kind of set that you would like to use. So hash set is the one most people will pick if they have no other reason to use a different kind of set. Right? The main operations of a set are add, remove, and contains. Right? So for hash set, all of those operations have O1 expected complexity. And if you think about that for a minute, that's kind of surprising. Right? So you can make a collection of, say, 1 billion elements, and that set can tell you whether or not it contains an element in constant time. Right? If there was a list, you'd have to look at all 1 million elements in the list. Right? And so it'd be in ON time. But for sets, for a hash set can normally answer that question in constant time. How all that works, you'll learn about in SYS 235, your data structures course. Right. Now, one of the trade-offs that a hash set makes to get this speed, you don't know the order of the elements in the set. Right? And so the hash set can reorder the elements however it wants to, or put the elements in whatever order it wants to. The user of the set doesn't actually know what order they are in. Right? You can loop over the set once and get the elements out. Right? You can then do some operations with the set and loop over the elements again, and it will be in a completely different order. Normally, your second alternative is tree set. So tree set keeps its elements in sorted order. Its add, remove, and contains method are all fast, but they're not as fast as hash set. Right? They have log n complexity. Right? So in 121, they should have told you what binary search is. Right? So you can binary search a sorted list, right, in less time than looking at every element in the list. Right? You can binary search a list in O log n time. Right? So it's not that surprising that you can search a sorted collection of stuff in O n time. Right? So it's not surprising that contains can be done in O log n time. Again, exactly how a tree set does this, you'll learn about in SYS 235. You might have learned about it in your math courses if you've seen a binary tree. Right. Okay, so in a tree set, your elements are in sorted order. Right. There is a third kind of set that is occasionally useful. So there's this thing called a linked hash set. So in a linked hash set, it's almost as fast as a hash set. Right? So it has the same complexity. In practice, it runs very slightly slower than a hash set. So like hash set, a linked hash set remembers what order you put things into the set. So in other words, if you iterate over the sequence of a linked hash set, you get the elements back out in the same order that you put them in. Right? And so the way this thing works is it's a hash set, but it's also a list inside. Right? So it keeps 2 copies of all your elements. Right? It keeps a list so that it remembers the insertion order, so that it can, when you iterate over the set, you get them back out in the same order that you put things in. Right? Now, obviously, the trade-off here is that it's keeping 2 copies of all the elements, and so it costs you more memory than just using a plain old hash set. All right. So there's no indexing in a set. So if you want to loop over the elements of a set for some reason, you have to use a for each loop. There's no other, a for each loop or something called an iterator, which we'll also talk about later in the course. So if you want to loop over a set of strings, then you just write a for each loop. Right? So for each string s in the set T, inside the loop, you can do something with s. All right, so what are sets good at doing? So sets are good at doing things like removing duplicates from a set, from a group of elements. Right? All right, so suppose I have a list and I want to find all the elements that occur 1 or more times. So I want to find all the duplicates. Right? If you want to do this on your own, what you end up doing is you end up writing a nested loop. Right? So you loop over the elements of the list. Right? And then you write another loop. Right? In the inner loop, you compare, in the inner loop, you loop over the elements of the list a second time. Right? And you compare the elements from the outer loop and the inner loop. Right? If they're equal, then you have duplicated elements. right? You have to make sure that you don't look at the same element in both loops, but basically you need a nested loop. Right? The other way to do this is to use a set. Right? So here I have a list of student account names. Right? So these would be your email addresses, for example. If I want to remove all the duplicates from this list, right, I can just make a set, right, and pass in the list. Right? And so sets will accept lists. The set constructors will accept lists as inputs. Right? It just looks at every element in the list and tries to add it to the set. Right? Whenever it finds a duplicate element, it refuses to add the duplicate to the set. Right? And so then you end up with the list of unique account names. Right? If you want the account names sorted, and I often want your account names sorted, or your last name sorted, or your first name sorted, right? You could use a tree set, right? And now this tree set takes care of sorting all the elements for you, and so that's nice. So now you get a sorted sequence of all the unique account names. And of course, if you want to remember what order the elements were in originally, you can use a linked hash set instead. All right, so I can find all of the unique account names. Is there a way to find all the duplicated account names? And so the answer is sure, yes you can. Use two sets. So I make a set of unique names, and I make a set of duplicate names. Right? And now I loop over the original list. Right? So CS account, that's my list of account names. Right? I call add on the set of unique account names. Right? So the add method returns true if the element is added to the set. Right? It returns false if the element is not added to the set. And so it won't add an element to the set if there is already an element in the set equal to the one you're trying to add. Right? So if not, add that account name to the unique accounts. That means that account is already in unique accounts. And so that means we want to put it into duplicate accounts. Right? And so you can add it to duplicate accounts. Right? If you try to add it more than once to duplicate accounts, the extra account names are not added. Right? And so now duplicate accounts contains all of the account names that were duplicated. Unique account includes all the account names that are unique. Here's an example of this loop in action. Right? So there's my list of account names. You can see that this person's name is duplicated and this person's name is duplicated. Right? So I'm going to loop over this list, and I'm just going to try to add them to unique account. Right? So starting with this one, that SP Kuma is not in unique accounts, so it goes into unique accounts. Right? That account name is not in here, so it goes into here. Right? This account name, not in here, so it goes into here. Right? Same with this one. Right? And now we get to SP Kuma again, right? And they're already here. So when we try to add it to this list, to this set, add returns false, and so we add it into duplicate accounts instead. Right? And similarly, when we get to depair it the second time, right? It's already in unique accounts, so add returns false when we try to add it to this set. Right? After it returns false, we can go ahead and add it to duplicated accounts here. Right? And so now you end up with the set of unique account names, right? And the set of duplicated account names over here. Sorry, I want, okay. All right, so I guess the last couple of lecture slides for today. So if you want to compute the union of two sets, there's a couple of ways to do it. So for example, I have a set containing the accounts of students who completed assignment 1. I have a second set of students who completed assignment 2, and I would like to know all of the students who completed either assignment 1 or assignment 2. Right? So that's the union of two sets. Right? So the method add all tries to add all of the elements from set 2 to set 1. Right? So in other words, it changes set 1 into the union of set 1 and set 2. Right? Sometimes you don't want to change set 1, but there's an easy way to deal with that. Right? So set 1 contains the accounts students who completed assignment 1. S2 contains the accounts of students who completed assignment 2, right? If I don't want to change S1 or S2, right, then what you do is you make a copy of S1, right? So I make a new set called either assignment. It's a copy of S1, right? And now I can add all the students who completed S2 to either assignment, right? And that leaves S1 unchanged, and it leaves S2 unchanged, right? And either assignment is now the set of all students who completed either assignment 1 or assignment 2, right? So there's the students who completed assignment 1. There's the students who completed assignment 2, right? There's my copy of S1, right? And so these are the students who have completed either assignment, right? Now all you do is you try to add these students to either assignment, right? So add all basically loops over these elements and tries to add it to here. So is SP Kuma already in the set? The answer is yes. So it doesn't re-add SP Kuma. Right? Is D parrot in this set? The answer is yes, so it doesn't re-add D parrot. Hugh Z is not in this set, so it adds it to here, and Dev C is not in this set, so it adds it to here. Right? It never looks at HP 1304 or Area 98. Right? It's looping over that set there. Right? And there's your set of students who have completed assignment, either assignment 1 or assignment 2. Right? It's the union of those two sets there. Right? All right, I guess that's a good place to stop. We'll complete the set and map lectures in the next lecture.